didn't know anything about what had been learned through the 60s and 70s about meteorite impact and the impact rates, because we had grown up with our textbooks which said that there indeed were bombarding asteroids and comets, but this was all in the early days, the so-called early bombardment of the Earth, and it was all over. And sure, Meteor Crater was probably an impact crater, but that's only one. It couldn't affect geologic history.
In 1980, Luis Alvarez, together with his son and colleagues at the University of California, Berkeley, came up with a very controversial theory. A thin layer of clay found at Gubbio in northern Italy marks the boundary between Cretaceous and Tertiary limestones, the so-called KT boundary layer. To explain why it contains 30 times more of the very rare element iridium than the layers above and below it, Alvarez argued that the Earth must have been hit by an extraterrestrial object containing that iridium. Quite different evidence of a strange event at the KT boundary came from scientists drilling the ocean bed to extract cores. The discovery is recalled by one of those scientists, Ken Su.
In 1980, I had been working with ocean sediments for more than 10 years. And during those years, we had developed techniques to make very precise determination of the age of the sediments. And we also developed a very new technique of getting the isotope composition of sediments from very, very small samples. And those two developments permitted myself to notice there was a major isotope anomaly at the Cretaceous-Tertiary boundary. And this perturbation suggested to us it was a very major environmental catastrophe which took place. That was the reason I got into this KT debate.
As an isotope geochemist, I became attracted to this debate by what Ken Su had noticed. He found that the ratio of carbon-13 to carbon-12 in the skeletons of tiny marine plankton fossils showed an abrupt change right at the KT boundary. Under normal conditions of photosynthesis, the living organic part of these plankton find it easier to use carbon-12 rather than carbon-13. As a result, more carbon-13 finds its way into their skeletons. But at the KT boundary, there is a major disruption of the oceanic carbon cycle. More than 95% of all marine surface water plankton with carbonate skeletons became extinct.
It was a global event, whether it's tropical or higher latitude polar waters. And we call this ocean the Strangenov Ocean in order to emphasize the ocean was almost devoid of living organisms.
With most of the plankton gone, there's absolutely nothing left to remove any of the carbon-12 from the surface waters of the ocean. Any surviving plankton that tried to grow new carbonate skeletons under these Strangelove conditions will contain more carbon-12 than normal. When we look at the carbon isotope record and the rocks that span the KT boundary, in this case at a site from Woodside Creek in New Zealand, we can see that the background Cretaceous values remain fairly constant. However, right at the KT boundary, they become dramatically more negative, what Ken Su has called the carbon isotope anomaly. Above the boundary, they gradually return to more normal values.
The period of time when the ocean was in this Strangelove state and almost devoid of surface organisms may only have lasted a few hundred or thousand years, but the recovery process took much longer. Alvarez and Su were not alone in realizing that something truly catastrophic may have occurred at the end of the Cretaceous.
It was actually a coincidence, and in the April of 1980, there were 4 papers published in 3 different journals, and all of them suggesting either an asteroid or a comet hit the Earth 65 million years ago and caused a mass extinction, such as the extinction of dinosaurs and of marine planktons.
Such a controversial idea has led to more than a decade of intense research and at times heated debate amongst scientists. Big questions had to be answered. Where did the asteroid hit? What effects did it have? Did it, as Alvarez suggested, cause a mass extinction that wiped out 80% of all species that were then living on the Earth?
Finding the big buried crater in Yucatan was a major step because we found the smoking gun. Really, we found the smoking cannon that produced the catastrophe at the end of the Cretaceous.
We join a team of latter-day crater hunters at the Lunar and Planetary Institute, Houston, Texas. Team leader Buck Sharpton recalls how the crater was discovered.
The surface expression is not at all what you would expect of a giant impact feature. It's completely covered by a veneer of Cenozoic rocks that have been laid down on top of it. Fortunately, the impact occurred right on the coast of what is the present coast of the Yucatan Peninsula. It's centered just about on the town of Progreso, located right here.
Since the crater was formed 65 million years ago, it's been buried under more than a kilometer of sediments. Finding it wasn't easy.
We have to rely on geophysical techniques of exploration, and the structure has actually been known of since 1950.
Petroleum companies prospecting for oil discovered a large circular anomaly in the gravity data they acquired as an aid to exploration. It was centered on Progreso.
This would be about where Progreso is, right here. So the coastline of the Yucatan Peninsula would run the northern coast along this line here, through the center of the crater, and then you're running right along the west coast, along the western edge of the map zone. And the thing that stands out, of course, is this deep depression, signifying a region where the gravity values are lower than normal.
Drilling into rocks where the impact crater should be produced geological cores of a rock type that was immediately recognizable to the scientists. This is very similar to the type of impact rock found at the Ries impact crater in Germany. It has abundant shock deformation evidence in it, including bits of melted and deformed rocks, and is a key sample for proving that Chicxulub is in fact an impact crater. And this sample, collected from about 200 meters below the impact rock, is completely melted. It can be dated radiometrically, and it shows that the age of the crater is indistinguishable from the KT boundary. Nearly 2,000 kilometers to the east of the impact site lies the island of Haiti, where a different kind of evidence for the impact was found.
At the KT boundary in Haiti, we've discovered first in 1991 glass spherules at the boundary, which are impact glasses. So they're of the order of about 8 millimeters in diameter, and they have a chemistry identical to that of glasses that are found in the Chicxulub crater. These spherules have been dated by argon-argon methods to about 64.5 million years, and again, they are exactly the same age as the Chicxulub glasses. So not only is their chemistry identical, but also their argon-argon age.
So finding glass spherules is a good way of tying a deposit to the impact. We're about 1,000 kilometers north of the Chicxulub impact site, in a region that in the late Cretaceous was a shallow marine platform under several hundred meters of seawater and was bounded to the west by the active volcanoes of the Sierra Madre. We join Ian Gilmore searching out some more evidence for what happened at the KT boundary.
"65 million years ago, I'd have been sat on the ocean bottom. What I wouldn't have expected to find on the sea floor are these massive sandstones that you can see behind me. Clues as to what they're doing here come from this layer of orange rocks that we can see underneath them and some interesting fossils.
A closer look shows the sandstone contains some large granules. Even closer, notice how well-rounded these granules are, a few millimeters in diameter. They turn out to be identical with those found in Haiti, glass spherules produced by the melting of the target rocks on impact and forming part of the ejecta from that impact. On the underside of some of the sandstone layers, there's a curious honeycomb pattern. It's very reminiscent of the boxwork from incinerated and so carbonized wood. Like this. More evidence occurs within the sandstone itself. These dark fragments are burnt pieces of wood. But how did they all get mixed up into the sandstone deposits?
In places, the sandstone is almost 5 meters thick. What's interesting about it is that it doesn't contain any signs of animal life, such as worm burrows. This tells us that these sandstones must have been laid down so quickly that life didn't have a chance to recolonize the sea floor. However, at the top of the sandstone is an even more important clue to their origin.
The top layer of the sandstone contains iridium, fallout from the vaporized asteroid. Whereas the impact melt ejecta, the material derived from Earth rocks, is found in the glassy spheral layer, several meters below. Where did all the intervening sand come from? And how did it get here so quickly between the two layers produced by fallout from the impact? Perhaps the most fascinating theory to emerge is that the sandstones are evidence for giant tsunami or tidal waves and were deposited in the short period of time between the arrival of the initial ejecta layer containing the spherules and the fallout of the iridium-containing layer from the impact's fireball.
The whole region was covered by a shallow sea. One would expect massive tsunamis to be produced by the impact event itself, and also tsunamis and earthquakes to be produced by the collapse of the crater. So the Gulf of Mexico must have been a very deadly place to be 65 million years ago.
Another 1,000 kilometers away from the point of impact takes us to the state of New Mexico in America. Rob Hoff, a research student at the Open University, joins Bruce Bohor of the US Geological Survey.
Well, that's the boundary.
So this is the boundary here, right.
Grayish-white streak is the ejecta layer, and it has a nice black coal above it, so it stands out well here.
Okay, got quite a dark grey clay below as well, yeah?
Because this event was so large, it's a different type of cratering than we have had experience with on Earth, at least as far as the ejecta layers are concerned. We don't have well-preserved ejecta from any other impact at this distance from the actual crater.
For much of the Cretaceous, central North America had been covered by sea. But by the time of the impact, this had receded, leaving behind broad, flat plains with streams meandering through them. Just the environment to preserve thin layers of sediment at the KT boundary, as we can see at the Raton Pass in New Mexico.
So this white layer here, Bruce, this is the ejecta layer, is it?
Yes, it's a white weathering clay stone. The second layer, the fireball layer, is directly on top of that. It looks yellowish here, overlain by a thin coal seam, which is the common occurrence here in the Raton Basin and other places in the western interior. When we talk about the KT boundary here, we have two layers. They're both from the same impact. The lower one consists of melted target rock, siliceous target rock that's been splashed out and deposited from an ejecta curtain in the atmosphere. So it's restricted in its distribution around the impact crater to about a 4,000 kilometer radius of Yucatan, where we think the impact occurred. However, the second layer that overlies it is called the fireball layer, and we find both of those layers, the thicker ejecta layer and the fireball layer, occur here in western interior sites. but at so-called far-field sites, ones over in Europe or in Asia and so forth. These two layers do not exist, and instead there's just a single layer. It consists of the fireball layer. That's the layer that went all the way around the Earth. Let's take a look at a piece of the melt ejecta layer that we collected yesterday.
So, what is thought to be the sequence of events at the KT boundary?
It seems like this was a very large object, an asteroid, at least 5 miles in diameter, which is approximately the size of Manhattan Island, and maybe somewhat larger. This caused an enormous shock wave, which went down and started excavating rocks from very deep below the impactor. It also caused the asteroid, the impactor, to vaporize because of its size and the speed of its impact and the shock that occurred as it hit the Earth. This vapor cloud rose up and penetrated through the atmosphere and began to disperse and circle the Earth above the atmosphere. Meanwhile, the crater itself was forming and ejecting melted target rocks. These were spread out and formed the melt ejecta layer, but the upper layer, the fireball layer, spread around the globe, and that is why we do find a layer representing the KT boundary at all points around the globe.
But there's a geological twist to the reason why the KT event was so catastrophic. After 100 meters of seawater, the asteroid hit sediments, limestones and sulfur-containing rocks called anhydrites. The spherules studied by Harald Sigurdsson are evidence of that. He found that they contain a relatively high sulfur content, up to 1% in weight.
It is the unusual geochemistry or unusual sediments at the impact site that determine the severity of this impact. And in a way, you might say that the impact hit the powder keg in creating the largest natural disaster that was conceivable. And we have estimated that as much as 10 to the 19 grams of sulfuric acid aerosol would have been emitted. And that is 5 orders of magnitude greater, for example, than the sulfur emitted by Tambora in 1815, which is the largest volcanic emission of sulfur that we know of. So 5 orders of magnitude, that is 100,000 times the mass that came out of Tambora.
Sigurdsson believes that the sulfur would have produced a long-lived sulfuric acid aerosol, resulting in the backscattering of solar radiation for several years after the impact, causing a global cooling of the Earth.
Preliminary models indicate that the cooling could have reached near freezing globally within a month, and that surface temperatures would have remained very low for several years.
The evidence for an impact is compelling, yet it still leaves one question unresolved. Did it cause a mass extinction? So what extinctions actually occurred at the KT boundary? Well, we know all about the dinosaurs, but marine sediments worldwide appear to show that many species of marine plankton were nearly wiped out, disappearing abruptly right at the boundary. To find out what happened on land, we have to look at fossil plants.
In terms of the different kinds of plants, most plants survive the boundary quite well. What the plants show is that there was a significant ecologic disruption. The palynologists, for example, had shown from the early 1980s that there was what they termed the fern spore spike at the boundary. And this is the sudden increase in abundance of a single kind of fern spore, at least a single kind at a particular locality, where it can go from perhaps less than 10% of all the pollen that a person finds in a sample up to in excess of 90%, almost 100%.
Jack Wolf believes that fossil plants indicate that the impact winter, as he calls it, lasted for perhaps 3 or 4 weeks. But 2 months after the impact, the ferns have reached their sporing stage again and leave their sign in the fossil record, the so-called fern spore spike.
What the palynologists likened this to was the recovery of devastated vegetation such as occurred at Krakatoa, the great Indonesian volcano that exploded in the last century, or the recovery vegetation on El Chichon in Mexico that blew its top several years ago. And so the ferns provided some evidence, this fern spore spike, of significant ecologic disruption.
Perhaps the greatest scientific debate surrounding the KT impact is whether or not the environmental changes associated with it somehow triggered the mass extinctions of land and marine life, which occurred at the end of the Cretaceous.
The dinosaurs became extinct right at the KT boundary. The smaller ones might have been able to, like lizards and turtles and snakes and crocodiles, could burrow into the mud and survive a short-term insult to the environment, sort of hibernate. Mammals were small rodent-like things that lived in the ground anyway, so they could also escape any atmospheric problems by being underground and surviving until plants reestablish themselves. So the survivors are the ones, I think, that you would predict by the type of catastrophe that the KT impact provided.
What is certain is that the controversy as to whether such catastrophic events determine major evolutionary change will occupy scientists for many years to come.
What the killing mechanism actually was is still elusive. If the rocks falling out of the sky could produce one extinction pulse, then I think we must expect, if not assume, that other extinction pulses also have been caused by this mechanism. And as Shoemaker has delightfully pointed out, when we realize that rocks do fall out of the sky on a regular basis, this becomes acceptable in a gradualistic framework, because it's part of the Earth's environment, which we accept and understand.